Okay, thanks, Dirk. Bruce Miller, VP Product Marketing for Xirrus, and we're going to talk next about real-world results that showcase some of the things we've been talking about here today. So we saw a lot of graphs and charts and things that talk about isolation. Obviously, we have thousands of customers running our products all the time, so we wanted to give an example of what some of them actually do, and then some of the testing that we've done actually first out there in the real world. So just to kind of start off, there is a problem with density today, and this is actually a picture of something that we found. That's a little bit dark there. Something that we found behind a set of stands in a college university. They were trying to get Wi-Fi to work across hundreds of people in an auditorium. There's obviously a problem when you have to do this because one AP wasn't cutting it, so they tried to staple 8 of them to a board and make it work. We actually have several examples of this that we've run across. I know in some of the other sessions earlier, the discussion about performance. Well, on average, you're not seeing a lot of data on an average AP, et cetera, et cetera. For the most part, that is the case. And as Xirrus, we're known as the high performance vendor, so you have a lot of vendors or customers come to us specifically to solve performance challenges. What we're seeing, the trend over just the last few years, is it's not just a large venue with thousands of people. Now it's even smaller venues. Schools certainly are running into this in their classrooms and auditoriums, but also you'll see it in high density enterprise environments. Stock exchanges or trading floors where you have literally 300, 500 knowledge workers all in one place, and they want to be mobile. They want to use their mobile devices, and those networks are starting to fall down. I can't just stick 6, 8, 10 APs all in one room and expect it to work. And this is what we see out there, and some of the things that we're talking about here is to address those kinds of challenges, obviously. So we've put together a performance test kit, and we've had this for several years, specifically to run through some of these kinds of tests. Some customers that we talk to, they want to ensure that what they're buying is a performance-ready solution, that it's going to meet some of the claims that we make or otherwise the requirements that they have. So we put together a test set to demonstrate some of these things. And this test bed actually consists of 100 plus netbooks, 2x2 11N devices. So they're not the fastest in the world, they're not the slower 1x1 phones either. They're somewhere in between. We've had this kit for a number of years. We actually have in our labs close to 700 different devices, MacBooks, iPods, iPhones, several hundred iPads. It's a pretty significant amount of equipment that we use to test. This particular set we actually packaged up in a road kit so we could take it out and run it in real-world scenarios on customer sites, or when it's not on the road, we park it back at our labs at headquarters. Yeah.
Now, I know I've been known to have some crappy wireless designs according to George, but even I know better that a real-world AP is not installed on a tripod sitting 5 feet from the...
Yeah, this is for photo purposes.
They're spread out quite a bit more.
Yeah, we tend to tread it.
I mean, you would typically, your guys' deployments you're putting into it as auditoriums, the array is going to be up pretty high. So
you get a wide enough angle on the camera.
Yeah. Minimum, well, we recommended a minimum. I'll show you a picture later where we actually have this at a university test, and it's obviously a wider space, so that's a good point. But yeah, we tend to provide a minimum guidance to our resellers who are using this kit. Don't jam it right in so that they're right on top of each other. So,
Bruce, I think the important question is, has that ever been mistaken for a bar stool in that configuration?
You have to be a pretty tall person.
Yeah, if you're a pretty tall person, possibly. But when you put it all the way down, it could double as one. So that's our kit. We use Ixia test software. I actually have a background from the test industry previously, so this is something that I helped to put together. And this is some results that came out of this. So to talk about and carry on to the isolation discussion that we had, and software programmable radios, and how does this all work together, what do you see in a real-world result? So this is a little bit of a mixture here of different things going on, but what we did in this specific test is we ran 2 radios, and we put a throughput test across those 2 radios with 10 clients, so 5 on each radio. Standard APs like the Xirrus products right here, you see in this specific case, of course throughput depends on distance and there's many things involved. These APs were getting a little over 100 meg. When I took 2 radios on a Xirrus array, And this is only partially loaded in this case, 2 out of 4 radios. You can see the multi-core processor and the performance. I got a nice little performance boost there. But then when I actually spun one of those 2.4 radios over to 5 gig, and I had a dual 5 gig, now I'm actually running even more throughput, well over 200 meg in this case. So we see the benefit of 5 gig over 2.4. And actually, if you just run the math real quick, if I take a 2.4 gig radio and say in normal scenarios I'm not bonding, right? So I'm just going to use 11N for this purpose, 2 by 2. This would be 150 meg, and a 5 gig radio would give me 300 meg, and that's 450. Of course, your mileage may vary, and of course the real numbers are going to be lower than this because you have the overhead of Wi-Fi. But I could get with 2 radios 450 meg total bandwidth. If I take that radio and switch it over to 5 gig, so now it's just 300 plus 300, and I have a 600 total megabit bandwidth. So the difference here between these two numbers is 33%. Okay, if I actually take a look at the difference between these two numbers here, it was about 24%. So we didn't quite achieve complete bandwidth of that, because there's obviously the radios are working within the chassis, but we obviously were benefiting from the overall throughput change that you saw here. Now when we move to 11AC, the numbers that Dirk put up there, it's actually 70% difference as opposed to 33, because I have so much more bandwidth available on the 5 gig. And so those kind of test results, then we would be interesting to see if we could achieve closer to the 70, which proves that the isolation is obviously being mitigated to a very large extent. This next chart actually shows this, where we actually even had some better results. This is what we call the density test. So we took all 100 of those laptops and we transferred a 100 megabyte file from the server to the laptop. And we did that as fast as possible until all 100 laptops got their 100 meg. So that was a 10 gig total transfer. And then we timed that. So you can see in this case, I had a couple 2 3x3 APs. I've obfuscated the vendor's name, but two APs there. One 4 radio array, so the same number of radios, all 3x3. And this was a mixture of 2.4 and 2.5. And now it's all 5 gig in this last case here. And you can see that the benefit of a greater and faster transfer allowed me to transfer the time, in this case 30% faster. So getting actually very, very close to this 33%. Yes?
I hate to be thick about it all, I'm sorry. But if you go back, what was it, 3 or 4 pictures where you had the pictures of all the APs stapled up on the wall and you said this doesn't work. Why not? At the end of the day, if you've got, let's say you've got 2 2.4 gigahertz radios hanging out right next to each other, one's on 1, one's on 6, you're telling me I'm going to get more throughput out of that if I put 1 on 1 and 1 on 11 because there's greater separation between the channels?
That will help.
But I guess I can't imagine that being dramatic. And so, I go back to that picture of the board where you've got, what was it, 8 APs, and you said, well, this obviously won't work. Well, why not?
That'll work, but it won't work well. You won't get anywhere near the multiplication of 8 radios, right, of throughput.
The challenge with this, and we've probably all seen people try to do this, stack APs, and what happens is a disaster. These antennas have no isolation antenna to antenna from this device to this device. These are Omni dipoles. What Avi went through and has painstakingly designed in this is so that even when 2 of these antennas are next to each other, there's a 40 dB isolation. To get 40 dB isolation between these 2 antennas, you've got to move these APs pretty far apart. And at 120 degrees, you're getting 60 dB isolation. That doesn't happen. The only way you get isolation between these antennas is distance. Or you start packing RF foam, or you use different antennas that are directional and develop the isolation for you. Standard rubber ducky dipole antennas stacked like that, no isolation.
You'll get adjacent channel interference on channels 1 and 11 if the APs are close enough.
Right.
Oh, yeah.
Yeah.
And 1 and 6, like my rule of thumb used to be 5 meters, and I know people say 2 or 3 meters when you're co-locating, but I mean that's not okay. You're saying you've seen that before, but you obviously can do other designs that are better,
Correct.
like you said.
This is a bit tongue-in-cheek. We actually we get a good giggle every time we find one of these in the field. We have found more than you would expect. As Bruce said, this was hiding behind the screen in a lecture hall, and we were called in to see if we could do better.
Right.
And in this case, they would have done better had they just spaced the APs around the lecture hall and tried to develop that 3 to 5 meters. But and the other challenge they have is this is a forced ratio of half 2.4 to half 5 gig. So in this case, with 8 APs, they're trying to use 8 2.4 gig radios. Even in the same room, spaced.
No, they're not. There's only 3 APs with 2.4 GHz radios and antennas.
Yeah, I think these three have the antennas.
Oh,
yeah.
my apologies.
That's
apologies.
why I'm asking, because those aren't all 2.4 GHz APs or 2.4 GHz radios, right? You've got one radio on a channel.
Right.
Right. There's no channel overlap in that scenario at all.
Adjacent channel interference questions that'll come up.
But the skirt is not enough.
Yeah.
You've got to develop further isolation. That's either by distance or by using different antennas.
No, I get that, but I guess what I'm asking is, are you really seeing that dramatic of an impact?
Yes.
Because when you're talking about inside of an array, you're talking about that close to each other, right?
It looks like that, but that's where AVI comes in.
No, I mean physical space inside of an array, right?
But it's physical space versus what's actually happening at the RF, what's really going on with the RF. When you have the directors and you have the reflectors and the directors that are creating the directionality, that's what's creating the isolation. The RF pattern on these rubber ducky antennas is just, imagine it's a giant donut.
No.
And there's no isolation there. There's no directivity. There's nothing that's going to develop any isolation between the antennas, and that's where spacing them apart works with dipoles. And if you look at the test results, you can see if I stack 4 APs on a table and run the test bed, that doesn't perform. If I put the 4 APs in the corners of a room and run that test bed, it does much better. You just simply got to develop the isolation between the APs.
Right. And in the results that we did here, we didn't do this. I mean, these tests here had the APs, for example, in the corner of the rooms. So we had one array in the middle. We spaced the APs out for distance to maximize, the efficiency of the design. We weren't cheating in that case. I think the main point here, though, is that you do get that isolation sufficient to give you the majority of the benefit that you would expect from the 5 gig versus 2.4 bandwidth in that specific case. Does that make sense?
Yeah, and again, I guess I was just under the impression that it wasn't. Adjacent channel interference obviously exists, but
yes,
I honestly didn't envision it to be that significant.
If you do, I only said that because I tested it because I was doing education deployments with Adult 11, well, it was early, but with G, you had to co-locate to support 30 kids in a classroom, and I wanted to know, because you'd read in a book, you'll get adjacent channel interference on 1 and 6 and 1 and 11 if they're close enough, and you'd read 2 to 3 meters. So I tested it, iPerf, different clients and APs, and I can't remember, it might have been up to 100 milliwatts, which is obviously higher than you'd have, but even I think up to say 25 milliwatts, you're still looking at 2 or 3 meters separation, and you get that significant decrease in throughput when you get it with adjacent channel, right, over co-channel. So that I saw enough that that was my rule of thumb. Then put the APs at least 5 meters apart. Maybe it could be 3.
Mm-hmm.
But I mean that's not but that's not even a typical. Yeah, I mean you guys are saying you've seen a lot, but obviously that could be designed with those Cisco APs much better.
Sure.
Right?
Correct.
Sure. Part of that was just to kind of point out the fact that there's a problem with density that people are trying to solve for.
Sure.
And all the discussion that we had about the isolation is really related to adjacent channel interference, not co-channel. Co-channel is between arrays, so when we get into a system design, then we use the directionality of the antennas to point channels away from each other. If I have 2 arrays both on channel 1, then I point one channel 1 this way and one this way, so that we minimize the interference between those arrays. Within a given array, it's all about ACI, or adjacent channel interference, where you have at least 20 dB separation based on the channel, And then, based on that other chart, we try to push that as far away as possible so that you minimize this impact of the skirt on the next channel. Here's one more test result. Just this is video quality, so the actual packet loss that you get from video, MLR is a test of that. If it's below 0.1 or 1, depending on what you look at, then you have good quality. In this case here, you can see where going from 2 2.4s and 2 5s to all 5 gig showed a significant drop in the MLR score. All of this actually was good video. This is actually 150 clients actually with 1 meg stream. So these scores are actually good video for all 3 cases. It just shows the impact and the benefit in this case of 5 gig. Cleaner spectrum, if there's neighbors with 2.4, those kind of noisy environments can impact your quality. Bottom line, 5 gig is better, a better place to be if you can get there. Okay, so we talked about this a little bit before as well. We went to a university. We had a customer who did a deployment with this test kit. They wanted to test multiple vendors. They tested 4 in total. We were one of the 4. This is, again, an example not how to deploy, and the local engineer, actually set up the APs this way, which obviously hurt them in that case. But the point, and if we're running this test, we would actually separate them. The point here, though, is that the results that we have from the test show what happens when you do this versus what happens when you separate them, which is obviously to the benefit of the test results. In this specific case,
just to be clear and to be fair, we delivered the test kit, set up our array, ran the tests, we left. The university invited other vendors to come in and use our test equipment and show how well they could do. One vendor came in and set their APs up this way. I swear to God, we didn't do that.
Yeah. But the point of the results then just shows what that actually, what that results in. And you can see in this case, they're not directly compared to each other side by side, but if I just point out the data test is that same test we did before with 100 clients all pushing 100 meg each. It took 14 minutes to pass the test there, while it was 6 minutes and 50 seconds in the Xirrus case, so about 2 to 1. So there was a huge break in that. Voice quality, if you're familiar with MOS scores, we had a good quality voice versus poor quality, and then they couldn't even pass the video test. So there was sufficient adjacent channel in that scenario that all of those APs sitting next to each other with omnidirectional patterns were not allowing the others next to them to, or they were stepping on them to the level where they were not sufficiently able to pass data effectively. And there's probably a lot of back-offs, collisions, errors if you would sniff the air and test that scenario out. So again, the impact of that co-location is a challenge. It's something that the design of the Xirrus array specifically points to be able to address these issues.
Before you go on, so
Yep.
your experience is very typical. A lot of people that we run into have tried what you've tried and putting APs and figuring out there needs to be a separation. And we run into this all the time when we're talking to customers. They'll take a look at our device and say, but they're this close. And physically, yes, if I take out a ruler, but when you take a look at how far apart they are in the RF world when they're isolated. So these tests, and what we're trying to explain here is that while common knowledge would say I can't put APs physically close together, you can with the right RF design. And in fact, even those other manufacturers with proper, if they used external antennas that were directional and they designed it, or they moved them apart, if you get enough isolation, it'll work. So this has been sort of one of the largest challenges we've had as a vendor, is to overcome that common knowledge that APs on top of each other don't work. APs on top of each other without proper isolation, without proper RF design, don't work. Built correctly, they can. So.
Right. So just to quick summarize that then is showing that the array architecture provides that better performance, the software programmability, which boosts the actual performance, and then the isolation, which allows the coexistence of the radios. So that was kind of the point of those tests, to showcase some of those things. And then the last thing we wanted to run through here is actual then customer examples of this. So real world scenarios from the events that are running around the world daily. We have quite a bit of equipment in large venues which I'm focusing on here. I mean, we cover a broad range of customer types, obviously, across the enterprise and everything, but we wanted to focus on the most challenging scenarios, which are the the convention centers and the places where you get tens of thousands of people at once. Microsoft is a customer of ours. Their events teams use our arrays and APs worldwide for dozens, if not close to hundreds of events every year. So there's, you may have heard of the PDCs, Professional Developers Conferences, the Tech Readies. There's quite a bit of these events that go on, all different sizes, and they've been using our products since 2008. Large scenarios, keynotes with tens of thousands of people, situations where they're running over 500 users on a single array, and I'll show you some example reports from some of these kinds of events in a little bit.
Actually, a question. The
Yes.
Web Summit in Dublin.
Pardon me?
The Web Summit event in Dublin.
Right.
Wi-Fi fell over, and when the venue was questioned about it, it's one of the larger tech events in Europe. And the press release that was issued that it was just upgraded the system with Xirrus arrays, but it wasn't able to cope.
Yeah, I know which one
about-
you're talking about. There was some design problems with the original design that went into that scenario that didn't accommodate for the final numbers of users that were going to be there. So when we go into a design, there's two primary things we look at. Is first of all, how many arrays and where do I put them from a placement perspective to provide coverage, and then how many radios do I have to provide the amount of capacity I need for the number of users. And in that specific case, the design did not accommodate the numbers of users that were actually on site. And
Okay.
so it caught the design off guard. We had to go back in there and rework
Yeah, I
some
mean,
of
the
that
thing
to
is
make it
that,
work.
like, for 2 years in a row, the Wi-Fi failed there. Like, you guys were obviously weren't involved in the
First one was another
first one.
vendor.
Yeah.
And the second one, we had to come in and retrofit the design because it was improperly set up the time we went in. So, yeah, I know one you're talking about.
Yeah, I know the guy organizing. I'm shouting on the phone at him to get it sorted out. But yeah.
Yeah. So I mean, we have those kind of events all the time. This one, if I understood right, was actually vendors literally almost shoulder to shoulder with multiple devices. So we weren't anticipating some of the numbers there, but you have to design properly with capacity. So
Absolutely.
do I bring in 500 radios or 1,000 or 100, right? And obviously there's a huge difference in cost, so you have to be savvy to that ahead of time. Here's an example, one of the more extreme numbers that we have, and this actually goes back a couple years. The numbers were even greater in 2013, but Salesforce is the biggest IT software conference in the world. I think this year actually, or 2013, it was over 100,000 people in Moscone. If you remember from Wirefield WFD5, we actually logged into the Moscone system live. There wasn't a lot going on, so we couldn't show you some really high numbers. But this is just an example of a conference that was there across a couple million square feet. 16,000 at the same time, 859 on one array at one time. So this is a 16 radio array with 850 users all doing internet access. Now, are they getting 50 meg SpeedNet tests? Of course not. They're all sharing the bandwidth on those radios, but they're all able to connect and do and transact, web browsing or otherwise. So this is the kind of density that we see in some of these events. They get very, very dense. 89 or 87 arrays across 16,000 people. You can kind of do the math there in terms of several hundred people on a given array, and some of them were obviously higher than others.
I just did the math. That's 15 devices per radio.
On average, right.
And yeah,
It's
which
not
is,
high density.
Well, that's on average, but if you take the 859 and divide that one out, that one's going to be over 50 on a 16, right? So when you look at the gross numbers, there's some of these arrays that are sitting in, cafe areas or lobby areas or what have you. But the keynote area that you see right there, 10,000, that was 20 devices, if I remember right. 24 devices. And so now you're talking several hundred on each array in that case. So yeah, there's, we talked about the Microsoft example. They have plenty of our APs. They go to a convention center, they'll put APs out in the peripheral areas, walkways, between convention areas, and they get, 5-10 users on them. So they buy an AP. You put the keynote scenario, then you're talking these guys with 8 radios or 16s, because that's obviously where the density is. So it's a mix and match deployment based on where you're at.
it's just the thought of having almost 11,000 people on Wi-Fi in one room is mind-boggling.
Sure is.
That gets pretty challenging.
So do you see, like, when people are deploying these arrays, do you see performance degradation? Like if I put one radio in an array and I performance test it, and I put 2 or 3 or 4 or 5 gig radios in that array, do you see a overall performance degradation or receive sensitivity hit based on just the amount of radios in the array?
You mean performance degradation, like just based on the throughput capacity of the array to
Not so much the array,
process the data, or?
In terms of like RF performance, like do I see a RF sensitivity drop? If I'm measuring client RSSI in an anionic chamber, and I put more arrays in the device, am I seeing like RF sensitivity decreases due to increase in
CCI?
I mean, you're getting
ACI.
As you turn on more radios, there's going to be more CCI. Obviously, there's elements of that in there, but yeah, I mean, what ultimately happens the way we design these networks is you actually take a bandwidth limiting 500K or a meg, and typically put that per user so that you don't have single users over hogging up the air. So we tend to spread it out so that you get a decent performance for everybody without somebody taking the whole thing down.
The other thing that happens is you start reducing your transmit power, you start increasing your receive sensitivity, trying to build much smaller cell sizes. To handle those 11,000 users in one room with 20 arrays, those were fairly small cell sizes. I mean, TX power is pretty low and RX sensitivity was high.
Yeah.
So you probably had a high noise floor in that room, but we got the RX sensitivity up as well.
Right.
That's
So
all.
is that user configurable?
Yes. Yeah, and there's an automated algorithm that'll do it for you, but you can also tweak it
Is
manually.
it changing the receive sensitivity or the CCA threshold?
It's doing both.
Right.
Yeah.
And that's a perfect time for you to ask the question from Twitter. There's somebody that was asking
Sure.
about how long does the automatic channel selection algorithm take to complete the scan?
Sure. So the automatic channel algorithm there's multiple flavors of it. There's the in-depth version of it would take, say, upwards of a minute to do a complete listen for a second or two on every channel, all radios tuned simultaneously, gather the traffic information. There are faster versions of that rely on the traffic information that's been collected in the background from the monitor radio or some of the other radios doing channel scans, and that can happen within a second or so. So there's depending on what you're doing during initial setup. The recommended approach, what the actual cloud solution will do is bring up one array at a time, do the full scan, get a complete picture of the environment, set that channel, leave it up and running, and bring up the next one. So very initial installation, you bring them up one at a time, and you get a great channel plan. And then you usually use the faster algorithm to do touch-ups.
And one more thing I remembered just from your question, we also have a capability that allows us to tune the transmit power down to -20 dBm, an ultra low power mode, specifically for the situation we talked about. So when you're in high density, you want to shrink your cells lower and lower to minimize the adjacent and the intra-array. So we actually have the ability to go lower than probably what other vendors have actually put in their products specifically for that purpose. So we can go from +20 to -20 and fine-tune those radios up or down to be able to specifically set it for those high-density scenarios where you usually have the smallest cell sizes you can get in those cases, because you're just trying to cover a specific area. You have no, you don't care about range at all in that case. So. One other customer, the Sands Expo. So these guys put in about 200 arrays across a couple million square feet. A competitor came in and quoted 1,500 APs. So that was a significant impact to them. They were able to save 1,300 locations. That was going to be months and months of install work. So you can't underestimate the impact of having lots of radios and fewer devices that can impact this kind of scenario. These guys ran the CES show just a few weeks ago, the second one they've done with Xirrus. So very high density scenarios here. They actually have some very interesting things that they're doing to monetize the network as well. So Justin Herman there is a great reference for us. He has plenty of different applications running over the Wi-Fi to push advertising, wayfinding applications, dynamic threshold marketing, and things like this. He said he was able to monetize or get an ROI on this network within literally several months because of all the services he provides, over the network. free access that's basic, but you want to pay for an upgrade, you can get more. And then obviously all the sponsorship capabilities over this kind of network as well. So this is an example of a Wi-Fi network where it's obviously way beyond just the connectivity and the access. It's what I'm doing with that, and public access networks in general are opportunities to engage directly with the user more and more.
Hey, Bruce. On all of these big events, is there a single integrator that does all of them? Is it you guys dealing directly with the...
It's typically an integrator that has the facilities to engineer and set it up. In many cases, we bring in special projects folks that we have on our teams that can help consult into that. But we try to pick partners and work with a array across the whole U.S. that has those skill sets.
And do you bless the higher visibility ones, or do you just...
In a lot of cases, we get involved, yes. Our senior engineering team will oftentimes review the designs. So it's really case by case. So, yeah, because these are the most specialized designs. I mean, to your point, they're not just cookie cutter. You're not designing them with our cloud-based system. You're really figuring out what the channel plan, the locations, the isolation is as best as you can. So I'm going to wrap up here with just a few charts. These are reports that are pulled from actual installations and operations that we had ongoing. A lot of them don't like to use their names, so I don't have any names of where these are at, but they're some of the largest companies in the world running these events around the world. These aren't even the extreme too. I don't have numbers specifically for that were in report form. Some of them, again, they don't like to share this information, but here is just an example of a typical kind of event, a 5-day trade show or a 4-day trade show, and you can see peak usage getting up to 10,000 users in this case across 89 arrays in this scenario. So you're over 100 in that point. So you have some very high density of usage across this network. Here's an example from that same, this is the same location where I have the individual numbers per array, and you can see on the right side there, max simultaneous stations. We have one array with almost 500 users on it. The highest I've seen is 859. I have reports from some people that they've had well over 1,000, on a given array. So it just shows the level of scale you can get with this type of architecture. Dirk alluded to this earlier. It's interesting to see the mixture of clients on different bands and how that's changing over time. If I go back 3-4 years ago, it definitely was a 2/3, 1/3, or 3/4, 1/4. 2.4 was dominant. Today we're seeing that sway. We're seeing in many cases well over half the clients 5 gig. It depends on where you are in the world. Sometimes that's still 2.4 dominated. In this specific case here, close to 60% of the stations were 5 gig capable. And based on the AC Express and the load balancing algorithms we have, we always push the clients to 5 gig wherever possible to optimize the bandwidth. Here was the application breakdown across over 5,000 users at this show. And you can see this was interesting in the sense that 16% of the traffic was Dropbox, actually. One of the things that we found out when we instantiated DPI on our arrays in our office, right, is how much Dropbox traffic there was at that time. And we, whether it's Box or Dropbox or otherwise, there's a lot of that kind of background traffic going on. Google, 32%. 11% was YouTube, so people watching YouTube videos while they're attending the conference. Maybe it's personal, maybe it's for business, I don't know. So just interesting kind of stats. This is we have 15 categories, and then we break out the applications by individual apps, and there's 1,200 apps we recognize, almost 1,300, and 15 categories that we categorize them in. But this gives you the visibility into what's going on, and then you can actually set policies. So I can go in there and say, I'm going to block all streaming media, or just Netflix, or I'm going to do that, for only certain times of the day between 8 and 5. You have very granular control to be able to set those policies per application or per application group to ensure that the mission critical or the business critical applications are actually working. Here's an example of a classification of stations. What type are they? And you can see in this case, no surprise, you're at a trade event with lots of users. Over half of them are using phones, and that Apple is very well represented here as well. Nearly 10,000 iPhones and over 4,000 iPads. So we tend to see over half the devices at these events, being Apple. A lot of Androids, obviously, as well. Just interesting stats when you kind of see and track this over time, how how this changes, because the devices are everywhere, tablets becoming more and more pervasive, less and less notebooks in many cases. People bring the tablets because it's a very mobile environment. And then as we saw, the shift to 5 gig with the iPhone 5, with a lot of the newer upper end phones, they're moving to 5, which is very good. Starting to adopt AC, which you have to have 5 gig support for, and they're moving in that direction. And then just some traffic, so aggregate traffic numbers. In this case, this was an event where you can see we're peaking at about 1.25 gig total traffic over the entire network. And you know, to your point, Keith, earlier in terms of numbers, you divide this out. This isn't going to be a huge number on a given array on a given device, because this could have been over 100 or 200 arrays. But the average sustained numbers is dramatically different from peak or flash traffic, as we call it, and that's something to understand as well. It's not just a matter that on average I get 10 meg on an AP from a performance perspective. When I have someone wanting to get his gig file downloaded now, or I have 30 students in a class firing up their laptops all at once, or I have an A380 parking at the gate in an airport and 500 people coming off all at the same time syncing up on their iPhone, those are flash traffic events that will take wireless networks to their knees. So it's not just a matter of designing for average utility or average usage. You have 10x, 20x scenarios that are baked into certain public access networks that you have to account for. Otherwise, you have situations where the network will completely fall to its knees. Okay, and that'll bring up a wrap to Wi-Fi to wireless field day 6. I think Lee has the decoder ring for this one, so he can probably tell you what that one actually says. But we wanted to thank everyone for attending here online, and the delegates here in the audience as well. It's been our pleasure to present to you today. And with that, I think we will call it a wrap. Or Stephen?
Yep, thank you. Can I ask just a couple questions real quick?
Sure.
Oh, sure.
So, do you have your antenna patterns available online publicly?
We don't have them in our data sheets. Mm-hmm. We share them with the customers as a request comes up.
Okay.
But we haven't traditionally published them.
And then my second question is, if you're sitting underneath an array, I understand there's isolation at the antenna level, but if you're sitting underneath an array, what's the CCI look like there at that level?
In the cone of silence.
Yeah.
Right.
Where you have a directional going out. Is my client dead underneath your array?
No.
You're close enough. The path loss is much smaller compared to when you're in a far distance.
And then am I hearing just every channel that array is pushing out?
Well, so it's less of an issue when you're trying to pass traffic, because when you get associated to one station and you're passing traffic, you can get maximum throughput even a couple of feet away from an array. The bigger issue we find that can potentially cause some issues is if you're literally right below an array and you hear every radio at the same RSSI. Some of these devices just get very roam happy. So that's where the load balancing algorithm comes in, try to keep them on a radio and try to keep them separated from other stations. So AC clients group together, 11N clients group together. So this is one of those areas back to the standards. We really need to work in the standards body and try to move the roaming decisions in enterprise applications away from the client back to the infrastructure. Mm-hmm. So it's far too often I see clients making illogical, dare I say, stupid roaming decisions, and either hopping onto radios that are suboptimal for it, either the wrong band, or hanging onto a radio for dear life when they've passed 2 others that would service them better.
Right.
And so that's the bigger issue.
And then is there any kind of measure of CCI underneath?
Once you get a couple of meters away, there's really no issue there. You've got
Thank you.
You're seeing.
Oh, sorry.
I was going to say you're seeing many channels, whether you're under the array or farther away. You're going to see multiple channels anyway, so it's the client's decision at that point what they're picking.
Right.
And it's going
always the client's
to be the
decision.
same, really. So
I had a question for maybe Avi could answer. Having surveyed hundreds of Xirrus sites with air magnet survey, walking back and forth, both outdoor and indoor, I don't see, when you click on individual radio MAC addresses, anything but omni patterns. There's slight slightly.
Well, you're in
They have a little lobe on one side. They pooch out a little bit on the side they're supposed to go, but they definitely go on the opposite side nearly as far. So that's my experience of what I've collected data. I was just wondering if you could explain
first
why
of
I
all-
see that.
First of all, you're in the far field, and you're in an indoor environment.
I've done outdoor
Oh,
too.
So you're not going to see, again, all the isolation effect are happening in the near field. But when you talk about the antenna gain, again, at 5 gigahertz, it's 5 dB gain. So those are not high gain numbers. But when you're in the far field that you're just going to walk around the array, you're going to notice some changes, but you're not going to see, major changes. But you're going to see directivity.
It'll look similar to the patterns. I mean,
Literally, I can tell you because I do a lot of the field testing too.
Yeah.
So definitely, I can see the directivity.
Because the near field is what you're measuring for your isolation locally.
Correct.
But clients are attaching to the far field. So they can be on the opposite side of one pointing this way and still being connected and sending data and having a good.
That can and does happen. As Avi was saying, even on the 2.4 gigahertz antennas are very low gain, maybe 2 dB directionality. So seeing 2 dB more in the front lobe versus the back lobe, unless you're being very careful and unless your device is good at measuring and taking into account multipath, it's going to look fairly omni, but it's got a lobe push that way. 5 gigahertz, a little more directional, but not much more. It's 5 to 6 dB. So you might see 5 or 6 dB difference being in front versus behind.
But that's really you'll see that at the edge. So if you're just going out to say neg 65, maybe you go 60 feet this way and 50 feet this way. Okay. So what I saw is what you've seen too. That was just a little confusing. Sometimes their marketing stuff has these nice little pictures,
yeah,
little wedgies. But what we see in the real world is they're all mostly omnis.
Well, if you remember the actual antenna patterns,
Yeah, they were fairly omni.
it is almost circular but shifted in one direction, and you also get some of these weird back lobes. But basically, it is going to work behind the radio, but you're going to be at any given point, 5 or 6 dB less at 5 gig than you are in front. So you're right. In 50, 60 feet away, that 5 or 6 dB isn't going to make a whole lot of difference in your connected experience.
So given that,
Yes.
then when you put two arrays next to each other, you only have so many channels, and you're going to end up getting co-channel interference. The CCI at split halfway between the two, even though this radio is pointing out on channel 6 and this is out on channel 6. In the middle, you could still get two channel 6s.
And for high density applications like we were just discussing, that's where channel planning and cell sizing is hypercritical. You can't just turn them on and leave everything up at max power and max sensitivity, because yes, you will cause problems. Take the example of the Dreamforce keynote where we've got 20 devices in one ballroom. You've got to go in and actually turn the powers down, turn the receive sensitivity up, and that was even when they're pointed away from each other, that buys you a collective, say 10 dB, but you still have to adjust the power.
Thank you.
How does it compare then? So if it's a slight increase, that's, I guess, depending on the type of beamforming, you can see slight increases, maybe a bit more significant. How does that compare? So if it's not quite omni, you're getting a bit of directionality. The one. And the same concept's really there for transmit beamforming. So how do the two? And will you guys, or I'm not even sure, is beamforming? I think it's mandatory in AC.
Mandatory wave 2.
Okay.
Right.
So
And how does it compare? This difficult to say at this point, but for prior generations, having some directionality, whether you gain it through beamforming or whether you gain it through a specific antenna, is a benefit in terms of being able to help you transmit at a longer distance.
Right.
The one potential benefit of doing it with a directional antenna versus trying to do the beamforming is the directional antenna gives you not only transmit gain outbound, gives you receive gain coming in, and it's a constant gain in one direction. The challenge you're going to find with beamforming is on the return path. I've seen other vendors that have not really beamforming so much as selectable antennas. The question is, which antenna are you listening to, and then how are you going to get your link balanced on the receive side? So, I think there's still going to be benefit to directional antennas even with transmit beamforming, because as you've pointed out, it's an omniball shifted to one side, but it does provide a benefit.
Oh, just a follow up for Avi. How much extra directionality did you pick up with the director on the AC antenna?
At 2.4, it's 3 to 4 dB,
Substantial.
which is quite a bit. Yeah. By the way, the issue about you're not going to see much of smart antennas with a cellular. It's traditionally most of the companies that try to go smart antennas in cellular or Wi-Fi that we know about failed. Mainly because the hardware becomes more expensive, the software, the overhead becomes more expensive, so people were not able to achieve that multipole effect of increasing the capacity so much by justifying to go to a smart antenna, investing so much more money in hardware and software to get to achieve better performance.
Right. Okay.
Yeah, but I'm sure in the future people will do that.
Cheaper.
We'll try again and get closer.